Hey guys, we are going to start chapter 6. This is our last chapter. If y'all remember in chapter 5, we talked about the second law of thermodynamics. We discussed the Kelvin-Planck statement, we talked about the Clausius statement, and then we also said that there was a statement related to entropy that dealt with the second law of thermodynamics. This entire chapter deals with entropy, and then as we go through, you'll see how it relates to that second law of thermodynamics. Now to get started, we are going to consider two internally reversible cycles, and I've drawn this picture here to show that. So we got state 1, state 2. First cycle, let's say it's this process A plus process C, so that'll be the first one. Alright, so that'll be one cycle. The second one is going to be process B plus C. So now we've got that. Now we're going to look at the Clausius inequality, which we talked about in the last chapter. And remember that using that inequality, if sigma for the cycle is equal to 0, then we have an internally reversible cycle. So don't forget that little detail that we talked about in the last chapter. Now, if we apply this Clausius inequality to these two cycles, let's see what we get. We're going to have this integral. We're going from state 1 to 2. Remember the equation was delta Q over T for the boundary of A. And then we're going to add to that the one for C. And don't worry, we're not actually going to solve these integrals. Now, if we're going to have reversible cycles, we already said sigma cycle has to equal 0. This was the equation for sigma cycle, so that means that summation there is going to be 0. And then if we do the same thing for the other cycle, the one where we had B and C, let's write that out. This time we'll have B, and then here we'll still have C. This is going to be 0 also. So now we've got the Clausius inequality written out for these two cycles, both reversible. That's why we made them equal to 0. Now both of these equations, if you look, they have this C term, right? So let's make a note about that. So both of the above equations have that integral for C. So since that's the case, and both of these summations here have to equal 0, then that means, since they both have this C term, then obviously the one for A has to equal the one for B. All right, so your Clausius inequality for A has to equal the one for B. Now we've got that. Okay. And what that's telling us is that the value of our integral depends on the end states, not the path that you use to get there. Because we took two different paths, right, to get from 1 to 2 and then back again, and we just proved using this that the path doesn't matter because this one has to equal this one, even though they are different paths. Okay, so the value of the integral is going to depend on your end states, so 1 and 2, not the path taken to get there. Alright, so now we've got that established. Now remember, a quantity is going to be a property if and only if its change in value between two states is independent of the process. Now, the integral above that we were just talking about, that represents the change in a property. And that change is going to be entropy. And our symbol for entropy is going to be S, so capital S. Now, if we want to write it out, basically we're saying the entropy of state 2 minus the entropy of state 1 equals the integral of delta Q over T, and this has to be for an internally reversible cycle, which is what we had. All right, so this is change in entropy. So change in entropy is equal to this integral here. Okay. Now, what we're going to do, we need to figure out what this really means, right? Because looking at this doesn't really help you know what it is. So the way that a lot of people describe entropy, which if you go online and you Google what is entropy, you'll see all sorts of arguments about what is entropy, what it's not. A lot of people introduce this as entropy being a measure of disorder in your system. So this is the way that I was taught it, so that's the explanation I'm going to give you guys. So when I think of this, I think about it as disorder in your system. Some people consider it as, they call it waste energy. It's energy you can't convert over to actual usable energy. But I always think of it as just disorder in the system. Now, remember, keep this in mind that it's disorder. So entropy of a substance is going to be the lowest in the solid phase, and it's going to be highest in the gas phase. And again, relate this to disorder, and this will make sense. So if you've got your molecules, you're in the solid phase, you got a lot less going on than you do with the molecules in the gas phase. Because in the gas phase, everything's moving around, bumping into each other, all sorts of stuff's going on. In the solid phase, not so much. So it's lowest in the solid phase, highest in the gas phase. So entropy is just disorder. Okay, think of it again as kind of energy, but it's just a measure of your disorder, how much disorder you have in your system. Now, keeping that in mind, let's go to the next page. So our change in entropy can be, let's write down what possible values are. We can have it be greater than 0, it can equal 0, or it can be less than 0. And our units that we're going to have kilojoules per Kelvin, and that makes sense. If you look at the equation, we had delta Q over T. Q is in kilojoules, T is kelvins. This is the SI system. English system, you'll usually have BTU per degree Rankine. And this is for regular old entropy. If you have specific entropy, which remember that would be the little s, this is capital S, you would have kilojoules per kilogram Kelvin or BTU per degree Rankine pound. And that's specific entropy. And this one will have the little s. So let's denote. So capital S, little s. All right. And entropy is found in the tables. I've shown you before that it was in the tables, and I said we'd cover it later. Now, that being said, it's got an equation that uses quality, just like enthalpy or specific volume or internal energy. And this is going to be for when we have that two-phase liquid-vapor mixture. So your specific entropy is going to be S equals SF plus X, which is our quality, times SG minus SF. And these are little s's For the large S's, I'll try to put these bars on the end so you can tell that it's a capital S. The tables, though, are going to give you the little s, specific entropy. All right, so this is going to be another equation you want to remember. It's just like the other ones. Nothing too new there. Now what we're going to do is we're going to develop our Tds equation. All right. So this is temperature and then change in entropy. Now, to do this, we're going to look at a compressible system that's undergoing an internally reversible process. We're going to neglect kinetic and potential energy because we don't need to worry about those. So if we look at delta Q, that's going to equal du plus delta work. And now let's define these terms. So delta Q is going to be equal to Tds. This is capital S. And the little delta work is going to be P times dV, where that's volume. Now we already said that ds is the integral of dq over t. Alright, so we've already got that. So now with this equation, we're just going to make some replacements. We're going to replace this delta Q with TDS, and du, that'll stay the same, and then delta W, which W's work, will be replaced with pressure times the change in volume. That's going to give us TDS equals delta U, that's a capital U by the way, plus pressure times change in volume. And then this is an equation that we have now. Now basically we replaced these little deltas with actual differentials here. And let's recall a few things. Enthalpy, the capital H, is going to be internal energy plus pressure times volume. So that means dH is going to be du plus dPV. And then let's go ahead and look at this part here. Let's extend this out. So that'll be du plus the pressure times dV plus the volume times dP. Alright, so now we got that. So we're just doing a little calculus here when we do the derivative of this product. We're going to go ahead and rearrange this. And when we do that, we get du plus pressure times the change in volume. That's going to equal dH minus the volume times dP. Now, if we have that, if we look at what we've got du plus pressure times dV. Now notice this is exactly what we had up here, right? So we can replace this with TDS. So T, or temperature, times our change in entropy here is going to be dH minus the volume times dP, where P is pressure. And now with that, if you want to write it on a unit mass basis, if you want to use the specific terms like specific entropy, specific enthalpy, and specific volume, then what you're going to get is the following. So let's put for specific terms, then we're going to get Td little s equals du, that's a little u, plus P times d little v. Alright, so we got that. That's just taking this equation, putting it in a per unit mass basis, and then if we do the same thing for this one, And we'll have Tds equals dH minus V dP. So now we've got these two equations. All right, so these will be the ones we use with the tables, because the tables give us the specific values. And let's call both of these equation 1. All right, so those together. Now these equations here that we just did, these can be used for any process. And by any process, I mean it can be reversible or irreversible. So it's not one or the other. You can use it for both. Okay, and that goes for these. All right, so we're already at almost 16 minutes in this video, so let's stop here, and then in the next one we will continue to develop more equations. And then eventually we'll get to the examples, and hopefully then you'll be able to see better what entropy is. See y'all in the next video.